This is my final project presentation for EE475. I'm doing machine learning for interfacial temperature prediction. So to begin with the problem, I have a side project doing solid-state metal additive, and that side project is shown on the right in this image compared to traditional metal additive. So I have some relative motion of this wire on the substrate. This has frictional heating, and the question I want to answer is, what is the temperature of the interface? How quickly can I find this temperature? Can the temperature at one location be used to predict the temperature at the interface? And of course, the overarching question is, can we use machine learning to do this? So here's the axisymmetric simulation I'm running. So I have a heat input between the wire and the substrate. I have boundary conditions on the substrate and the wire, and I'm varying both the heat input, the substrate thickness, and the substrate radius. So the simulation can determine the temperature at the interface. It can't really do the inverse problem of temperature at B to predict A. But we'll do that in machine learning. And this can be slow to run and requires some skill. So if we can get a machine learning function, we can have a simple to evaluate function in Python to give the answer quickly. So for data collection, obviously we need lots of data for ML training. I found 600 data points. So this was 4 sets of the radii, 4 sets of thicknesses, 30 sets of heat inputs. So it's just a full factorial investigation. The simulation ran in ANSYS Mechanical, which you can see on the right. This is a temperature distribution on a mesh, and the parameters were set up in ANSYS Workbench so that it just took several hours, but it just did all the simulations for me. The model that I went with was machine learning neural network units. So these are this tanh function, and you can see the 3 parameters, the radius, thickness, and either input power or temperature at location B as those x1, x2, x3, and I use gradient descent to optimize all these weights. So the first result, I use the power as one of the inputs and predict the temperature at the interface. So I use 20% of the data to do validation, and I trained using 500 iterations with a 0.01 step size. And you can see from this image, I use from 1 to 40 units, so you can see the result improving as I increase the number of neural network units, and there's no overfitting, as you can see from the validation closely matching the training data. And the model that was found can quickly perform inference. So in this case, I'm asking it what the temperature at the interface is given a radius of 14, thickness of 5, and power input of 102 watts. And it spits that answer out very quickly. The second result is using the temperature at location B as the input. So last time there was no overfitting, so assuming that again, I directly just optimize 50 neural network units. I have to use more iterations and a smaller step size, but this gets me to an acceptable error. And still we can do rapid inference, and we're even addressing this inverse problem that we didn't directly model. So we can ask it, if a substrate has a radius of 15, thickness of 5, and the temperature that's measured at point B is 60, what is the temperature at the interface? And it gives us that answer right away. So to conclude, I use nonlinear machine learning to predict interfacial temperature in an engineering problem. The training data came from these 600 simulated conditions. Neural network units were sufficient to approximate the behavior after only 40 or 50 units. And 2 models were generated. The first predicts the interfacial temperature given a power input, which is the Ford problem, and the second one predicts the interfacial temperature given a temperature input, a measured temperature input. This is the inverse problem. So in the future, we could make the problem more detailed, try to do a transient simulation to better capture the actual friction physics, and we could even just add more parameters like wire diameter or wire length. Thank you.